A wave represents the transfer of energy through a medium. However, we can observe the motion through this medium. We can hear sound waves. We can see light reflect off of objects. We can observe the crests and troughs of a regular mechanical water wave. Although the medium doesn't move, we're able to calculate the speed of the wave. The basics of the speed of a wave you learned when you were young. When you first started walking and eventually running, you realized that if you increase the number of steps per second, you move faster. This is the difference between walking and jogging or running. We would call this the frequency. It's the steps per second. You also learned that if you increase the length of your stride, you're going to increase your speed as well, or change your speed. We could look at this as the wavelength. Keep those basic observations in mind as we move forward. There are 3 different methods for calculating the speed of a wave based on the information that you're given. Method 1. This is similar to how we measured the average velocity of any object. We measure the time it takes a crest to travel a known distance. We usually would use crest, but you could find any point on that wave and find from where it started to where that point ended. That's your distance. That's how far the wave has traveled. So we calculate distance over time. We know how far the wave traveled. We know how long it took to get there. When I divide those, it'll give me the speed or velocity of the wave. Let's try an example problem. The crest of a water wave travels 7 meters in 20 seconds. How fast is the wave traveling? The crest being the upper peak of the waves. This is the wave that you see peeking out of the water. We're going to take velocity equals distance over time. I know this because I was given a distance, I was given a measure of time, and I'm going to divide them out. 7 divided by 20 gives me 0.35 meters per second. The word problem or scenario told me the information I needed to figure out the right formula to use, and then it had the right given information to substitute in. At that point, it's just plugging and chugging. The second method goes into what we discussed about running. The frequency with waves is the number of waves or pulses passing a certain point per second. We talked about frequency when we talked about centripetal force. In that scenario, instead of waves or pulses per second, we were dealing with revolutions per second. Regardless, the variable for frequency is a lowercase f. The unit is going to be waves or pulses per second, or hertz, which you can shorten down to capital H, lowercase z. As we discussed earlier, the frequency, the number of waves, or if you're running, the number of steps per second, interact with how long your stride or how long your wave is. If I multiply the frequency times the wavelength, I'll get the speed or velocity of the wave. Let's look at an example using method 2. A sound wave is 1.13 meters long and has a frequency of 301 hertz. How fast is the sound wave moving? We look at the information that's present. I'm given a wavelength and I'm given frequency. I know it's frequency because it says frequency. I also see the unit hertz, Hz. I might also, in a scenario like this, be given waves per second or pulses per second. If you're given number of waves and an amount of time, you can simply divide number of waves divided by time. I set up my formula. Velocity equals frequency times the wavelength. Now I just need to substitute in the values that I already know. I know the frequency is 301. I know the wavelength is 1.5. Now I just need to plug and chug. It's a simple one operation equation. 301 times 1.5 gives me 451.5 meters per second. I chose the formula based on the information. I knew I had frequency and wavelength. I have a formula that uses frequency and wavelength. I substituted in the given information and then I just plug and chug. Always ask if your answer is reasonable or not. A small ripple in a pool is probably going to be moving a lot slower than a sound wave. The third method is related to the second method. The period of a wave is the time it takes to generate a single wave. So, Period, we know, is equal to time divided by number of waves, which means it's just the inverse of frequency. So if I have the amount of time for a single wave and the number of waves, I can calculate the period. If I have the frequency, I can also calculate the period by taking 1 divided by my frequency, or using caret -1, or if your calculator has an exponent of -1, an inverse key. We represent the period with a capital letter T. That's because it's a special variation on time. It's the amount of time per wave. The unit is going to be in seconds. If we're given, or if we calculate the period, we just need to do period divided by wavelength. This will give us the speed or velocity of our wave. Consider an example of a wave pool. It creates 5 water waves every 30 seconds that are 1.5 meters from crest to crest. How fast are the waves moving? In this case, we need to start by finding whether we have our frequency or whether we have our period. Because they're inverses, we could find either. Let's find the period. The period is time per wave. So that's 30 seconds per 5 water waves. So I can find my formula, period divided by wavelength. 30 seconds divided by 5 waves would give my period. So I could either plug in 6 for my period, or I can plug in 30 divided by 5. Now I just plug and chug. 30 divided by 5 is 6. 6 divided by 1.5 gives me 4 meters per second. Always check if you're reasonable. This is a relatively low velocity compared to a much faster moving sound wave. Anytime that we can use formulas to solve for one variable, we can always use them to solve for others. Up to this point, we've just been substituting in. That gives us the speed or velocity of our wave each time. If we wanted to find the wavelength, the frequency, the number of waves, we would need to start with the speed of the wave and then solve, using other given information, solve for the unknown. So always choose the proper equation. A proper equation includes the given information and the information that's unknown, the information that you're looking for. Substitute the values into the equation. Now, when you choose your equation, you have the option of choosing the original equation, which you can still substitute into. You'll just have to solve. Because these are all 3 variables, you're really just going to be doing one-step equations. You're either going to be multiplying by a known or dividing by a known. The other option is to use a derived set of equations. In this case, the variable you're looking for is already solved. It's already by itself. This makes the math more approachable. You'd substitute values in to evaluate instead of using inverse operations to solve. Once you've substituted in, you can either evaluate or solve, depending on whether you've used a derived equation or the original equation. Let's try an example with an original equation. A wave is moving 4.5 meters per second. If it has a wavelength of 0.8 meters, what is its frequency? I need to choose the proper equation. I'm given the speed of the wave, 4.5 meters per second. I'm given the wavelength and I'm given the frequency. I need to find a formula that has the speed, wavelength, and frequency all in one formula. I'm going to use the original formula, velocity equals frequency times wavelength. Substitute the information I know in. The velocity is 4.5 meters per second, the frequency is unknown, and the wavelength is 0.8 meters. In this case, I have frequency times 0.8 equals 4.5. I need to get frequency by itself. I'm multiplying my unknown by 0.8, so I would divide both sides by 0.8. 4.5 divided by 0.8 gives me 5.626 hertz, or 5.626 waves per second. For example 2, let's use one of our derived equations. A wave is moving at 3 meters per second. It has a period of 0.5 seconds. What is the wavelength? So we're given the speed of the wave, we're given the period of the wave, we're looking for the wavelength. So we need a formula that involves wavelength, period, and velocity. I also, because I have a derived set of equations, want to find a formula that has wavelength by itself. In this case, I could use wavelength equals period divided by velocity. Now I'm just going to substitute that information in. Wavelength equals 0.5 for the period, 3 is the velocity, and I just divide. 0.5 divided by 3 gives me 0.1667 meters. That's how long the wave is from crest to crest, from trough to trough, or from node to node. The speed is always based on the information given. So finding the individual variables is always based on the information given. Choose your formula wisely. Make sure you substitute everything in, and make sure you either evaluate or solve for the correct value or correct variable. If it's asking for wavelength, make sure you give a wavelength with proper units. If it's asking for frequency, make sure you give a proper frequency with proper units.